Dear students, welcome to EPG Pathshala. Today, we are going to discuss on geothermal energy. In this module, we will be learning about geothermal energy, which is Earth's heat. This is the thermal energy present inside the Earth. We all know that inside the Earth, the temperature is very high. And some visual symbols are there like volcanoes, geysers, hot springs, etc. There are different countries working on the harnessing methods for the geothermal energy to cope up with the depletion to overcome the fossil fuel problems. In this module, we will be dealing with the global scenario of this geothermal energy as well as Indian scenario. We will be focusing on the potential of geothermal energy in India. In this module, we will see the energy inside the earth formation and the formation of geothermal reservoir, classification of the geothermal resources, different types of geothermal plants, the natural reservoir as well as the man-made reservoir. We will also see the limitation as well as the advantages of this geothermal energy. Let's see what is geothermal energy. Geothermal comes from the Greek words geo, which means earth, and therm, which means heat. So, geothermal means earth heat. It is the heat contained in the rock and fluid. Fluid means that fills the fractures and pores within the rock in the earth crust. So, this is the thermal energy present in the interior of the earth. This geothermal energy resources range from shallow groundwater and hot rock in the deep crust of the earth to the extremely high temperatures of molten rock, which is called magma, at interior of the earth. Let's see energy inside the earth. We all know the earth is divided into three parts: core, mantle and crust. The earth's core lies almost 4,000 miles beneath the earth's surface. The double layered core is made up of very hot molten iron which is surrounding a solid iron center. Estimates of the temperature of the core range from 2800 to 6000 degrees Celsius. The geothermal energy continuously produced within the earth by slow radioactive decay of minerals, which is natural in all rocks. Surrounding the earth's core is the mantle, thought to be partly rocky and partly magma. The mantle is about 1800 miles thick. The crust is the outermost layer of the earth, the land that forms the continents and ocean floors. It can 3 to 5 miles thick under the oceans and 15 to 35 miles thick on the continents. The earth's crust is broken into pieces called plates. Magma, the molten rock, may come quite close to the surface where the crust has been thinned, faulted or fractured by plate tectonics. This is where volcanoes occur. The lava that erupts from volcanoes is partly magma. Deep underground, the rocks and water absorb the heat from this magma. When this near surface heat is transferred to water, a usable form of geothermal energy is created. The temperature of the rocks and water get hotter and hotter as you go deeper underground. Let's see how the geothermal reservoir is formed. The earth's temperature increases with depth, with the temperature at the center reaching more than 4200 degrees centigrade. A portion of this heat is the residue or the remains of the planet's formation about 4.5 billion years ago, and a portion is generated by the continuing decay of radioactive isotopes. Because of this, geologic processes are known as plate tectonics. The earth's crust has been broken into 12 huge plates that move apart. When two plates collide, one plate can thrust below the other, producing extraordinary phenomena such as ocean trenches or strong earthquakes. At great depth, just above the downgoing plate, temperatures become high enough to melt rock, forming the magma. Because magma is less dense than the surrounding rocks, it moves up toward the earth's crust and carries heat from below. Sometimes magma rises to the surface through thin or fractured crust as lava. However, most magma remains below Earth's crust and heats the surrounding rocks and subterranean water. Some of this water comes all the way up to the surface through faults and cracks in the earth as hot springs or geysers. You can see in this figure the hot springs and the geysers, the flow of this one. When this rising hot water and steam is trapped in permeable rocks under a layer of impermeable rocks, it is known as geothermal reservoir. These reservoirs are sources of geothermal energy that can potentially be tapped for electricity generation or direct use application. Let's see the classification of geothermal resources. Based on the temperature, normally it is known by enthalpy. The geothermal resources are divided into three categories: low enthalpy resources, medium enthalpy resources and high enthalpy resources. Low enthalpy resources have a temperature below 125 degrees centigrade. Medium has a temperature of 125 to 225 degrees Celsius. And the high enthalpy resources are those with temperature greater than 225 degrees centigrade. In this graph or the schematic diagram, you can see the depth temperature plot for geothermal resources. Coming to the uses of geothermal energy. A naturally occurring geothermal system, which is known as hydrothermal system. It is defined by three key elements: heat, fluid and permeability at depth. Some applications of geothermal energy use the Earth's temperatures near the surface, while others require drilling miles into the Earth. The three main uses of geothermal energy are direct use, that is for the heating system, which use the hot water from springs or reservoirs near the surface. Electricity generation in a power plant requires water or steam at very high temperature. Geothermal power plants are generally built where geothermal reservoirs are located within a mile or two of the surface. The third use is geothermal heat pumps, which use stable ground or water temperatures near the Earth's surface for comfort, cooling or heating of the buildings. Let's see in detail about geothermal power. Geothermal is a base load power source. What is a base load power source? It is a plant that produces energy at a constant rate. You can say nuclear as well as coal-fired plant are also base load power source because it produces at a constant rate while the solar energy is not. Because this energy is constant, the power output can remain consistent nearly 24 hours a day, giving geothermal energy higher capacity factor than the solar or wind power, which are dependent on sun to shine or wind to blow. Geothermal power is the electricity generated from the heat source, that is the magma within the earth crust. Geothermal power plants use hydrothermal sources which have two common ingredients: water, that is hydro, and heat, the thermal one. Geothermal plants require high temperature hydrothermal resources, as we have already seen, that may come from either dry steam wells or hot water wells. We can use these resources by drilling wells into the earth and piping the steam or hot water to the surface. We will see in the later slides in detail. The power plants use steam to power a turbine which creates electricity. If you look into the global scenario of the status of geothermal energy, we can see that the total installed capacity for global geothermal power generation was estimated to be around 12.8 gigawatts. The top 5 leading countries in this power generation are USA, Philippines, Indonesia, Mexico and New Zealand. The total installed capacity of geothermal for the direct utilization over the world is around 70.3 gigawatt. And in that case, the leading, where the low temperature is available, the leading countries with the largest capacity of geothermal direct utilization are China, USA, Sweden, Turkey, Germany, France, Japan and Iceland. Coming to the Indian scenario, in India, preliminary assessments have indicated prospects of development of geothermal power. Systematic efforts to explore geothermal energy resources started in 1973 and preliminary assessments suggest that India is in low and medium heat enthalpy zone. 340 hot springs have identified by the Geological Survey of India in different parts of India with surface temperature ranges from 35 to 98 degrees Celsius. 31 areas have been examined in detail and shallow drilling has been done in 16 areas. If you see the potential of geothermal in India, geothermal exploration carried out by exploratory drilling at selected geothermal locations such as Puga, that is in Ladakh, Manikaran, Tatapani, Tapovan, Campe, etc. relating to the structural, geological, geochemical, hydrological and thermal parameters of these geothermal systems. The hot springs present in the country are grouped into 7 geothermal provinces. The 7 geothermal provinces are Himalayan Puga Chumtang Province, Sohana Valley, Campe Basin, Sun Narmada Tabi Lineament Belt, that is Sonata, West Coast, Godavari Basin and Mahanadi Basin. In this table, you can see the thermal characteristics of the above potential geothermal provinces, and in that the Himalayan province has the highest one. Coming into the geothermal power plants, you can see that there are 2 types of geothermal power plants. The major one is the hydrothermal reservoir, which is a natural reservoir. These hydrothermal resources are formed when underground water has access to high temperature, porous rocks capped by a layer of solid impervious rock. The entrapped water is heated by surrounding rocks. The hydrothermal resources can be classified depending on the heating of entrapped water as dry steam fields or vapor dominated resources, wet steam fields or liquid dominated resource and hot water resource. So, we have seen that wells are drilled to bring geothermal energy to the surface, where it is converted into electricity. There are 3 basic types of geothermal power plants. You have dry steam plants, flash steam plants and binary power plants. Dry steam plants use steam piped directly from a geothermal reservoir to turn the generator turbines. Flash steam plants take high pressure hot water from deep inside the earth and convert it to steam to drive the generator turbines. When the steam cools, it condenses to water and is injected back into the ground to be used over and over again. Most geothermal power plants are flash plants. The third type, binary power plants, transfer the heat from geothermal hot water to another liquid. The heat causes the second liquid to turn to steam, which is used to drive a generator turbine. Let's see one by one in detail. Dry steam geothermal power plant. It is also known as vapor dominated plant. It's in the dry steam geothermal plant. It's a power plant in which steam generated underground by geothermal heat is used directly, thus eliminating the need for boilers and boiler fuel that characterize other steam power generating technologies. Water boils underground in a hydrothermal resource when it has a pressure of about 7 atom and temperature of about 165 degrees centigrade. The dry steam fields are located at the geysers region of California, Matsukawa region of Japan, etc. The plant consists of production well to extract steam from the hydrothermal resource, a centrifuge separator to remove solid matter from the steam, a turbine to convert thermal energy into mechanical energy, a generator coupled to turbine to generate electric power, a condenser to condense wet steam excited from turbine into water by direct contact with cooling water, and a cooling tower to cool water excited from condenser and returning the cool water to the condenser. You can see the schematic diagram of the dry steam geothermal plant where steam rising is there, and this steam runs the turbine, while after the production or after trapping the steam, the water content is condensed by the condenser and that water is re-injected into the earth crust. The second type is flash steam geothermal plant. It is also known as wet steam or liquid dominated geothermal plant. When the temperature of hydrothermal liquids is over 177 degrees Celsius, flash steam technology is generally employed. I have already told you this is the most common type of geothermal plant. In these systems, most of the liquid is flashed to steam. The steam is separated from the remaining liquid and used to drive a turbine generator, while the water is returned to the geothermal reservoir. You can see in the schematic diagram, earlier you have seen that from the production well steam rises. Here the hot water rises and the steam is trapped to turn the turbine, while at the same time or simultaneously you can say the water is re-injected. So, this water is not directly after earlier we have seen that the steam passes the turbine and then comes to the condenser, but here the brine water or whatever this is re-injected to the injection well. The third type is binary cycle based geothermal plant. Binary cycle power plant are used with hot water that is at a lower temperature than that which supplies steam plants. Such lower temperature resources are much more common for the direct heating. The hot water is passed through a heat exchanger in conjunction with a secondary. This is known as binary plant also. Fluid, this is a secondary fluid. Here a secondary fluid is introduced with a very low boiling point. This secondary fluid normally is a hydrocarbon such as isobutane or isopentane. The secondary fluid vaporizes, which turns the turbines which drive the generator. The remaining secondary fluid is simply recycled through the heat exchanger. The geothermal fluid is condensed and returned to the reservoir. So, in this schematic diagram, you have an additional heat exchanger. And here, what happens? You have a secondary fluid which is isopentane or isobutane. It traps the steam and then it is used for the generation of electricity or by turning the turbines. While after its usage, this secondary fluid is recycled in this system or in this type of cycle. Now, you have enhanced geothermal system. It is also known as EGS system. EGS is a man-made reservoir created where there is hot rock but insufficient or little natural permeability or fluid saturation occur. It is also known as hot dry rock resources, which in short HDR. In an EGS, fluid is injected into the subsurface under carefully controlled conditions which cause pre-existing fractures to reopen, creating the permeability. Enhanced geothermal systems utilize advanced, often experimental drilling and fluid injection techniques to augment and expand the availability of geothermal resources, which can be used to generate electricity from the heat in the Earth's crust. Enhanced geothermal systems, when recharged, can produce near continuous output, making the technology a renewable zero carbon option for supplying base load electricity production. This type of system still remains a topic of R&D with some pilot projects. This is the schematic diagram of the working of enhanced geothermal system. Coming into the efforts in the development of geothermal potential in India. Research, development and demonstration program for utilization of geothermal energy for power generation and direct heat applications was supported by Ministry of New and Renewable Energy, that is MNRE, through direct organizations like IIT Delhi, NAL, National Aeronautical Laboratory Bangalore, Geological Survey of India, National Geophysical Research Institute Hyderabad and National Hydroelectric Power Corporation Faridabad. And the main achievements are: a cold storage plant was constructed in the 80s by IIT Delhi in Manikaran, Himachal Pradesh to utilize geothermal energy at 90 degrees Celsius for preserving vegetables and fruit grown in that area. An experimental geothermal power plant of 5 kilowatt capacity was set up by NAL in 1992 at Manikaran in Himachal Pradesh. The power plant was operational for some time but was subsequently damaged by a landslide. An R&D project was undertaken in 1997 by the Regional Research Laboratory, Jammu, for utilizing geothermal energy for mushroom cultivation and poultry farming in Puga, Ladakh region of Jammu Kashmir. One 30 into 20 feet insulated hut was constructed and temperature of the hut was maintained at 20 to 25 degrees Celsius using heat from the nearby geothermal wells in Puga. Magnetotelluric studies were assigned to National Geophysical Research Institute in 1999 to assess the deep reservoir temperature of potential sites at Puga geothermal field located in northwest Himalayan range in Ladakh. Tatapani geothermal field in the Sarguja district of Chhattisgarh also done some studies. If you see, in Puga geothermal field, the presence of geothermal reservoir is at a depth of about 1.5 to 2 km. The estimated depth of geothermal reservoir is about 4 to 5 km. In the Tatapani geothermal field, the hot spring area is underlain by a highly conductive subsurface section related to a major geothermal reservoir. The estimated temperature at deeper layer, that is 3 km, is about 260 degrees Celsius. We can also see there are some few installations of geo-exchange based heating and cooling system. Geothermal heat pumps at Tripada International School, Gujarat by Geoclinic, Ahmedabad. Indira Peryavaran Bhavan in Delhi. 32 TR capacity systems in Swaminarayan Temple, Dholera, Gujarat. Now, what is this ground source heat pumps or GSHPs? The ground source heat pumps are also known as ground heat pumps, ground coupled heat pumps, ground water heat pump and geo exchange pumps. These use the earth's relatively constant temperature between the range of 16 to 29 degrees Celsius all over round at a depth of 20 feet. Consider the ground as a readily available renewable storage battery for heat. The temperature in the ground below 6 meter is roughly equal to the mean annual air temperature at that latitude at the surface. This GSHP provides heating, cooling and hot water for homes and commercial buildings. It is effective in all kinds of climatic zones and deployed anywhere in India. So, this GSHP use the earth as heat source in the winter or a heat sink in the summer. Throughout the winter, the water is warmer than the outside temperature. So, the geo-exchange system extracts heat from the water to distribute throughout the building and cool water is returned to the earth to be rewarmed. The system is reversed in the case of summer. Now, coming to the advantages of geothermal energy. It is a reliable source of energy. It is in continuous supply. Its availability is independent of weather. It has an inherent storage capability and does not require any storage device. Small space is required to install the plant. It is least polluting and does not require any supply fuel to generate heat. But it has some limitations. Geothermal energy is available as low grade heat. That is, the temperature of geothermal fluid is very low. These fluids also bring dissolved gases and solute which lead to air and land pollution. Removal of heated water from the hydrothermal reservoir may lead to land subsidence or seismic imbalance. Geothermal energy cannot be transported for very long distance. That is, it is concentrated in area less than 30 kilometers from its origin. The life of plant equipment is limited due to corrosive and abrasive nature of geothermal fluids. So, to summarize, in this module we have seen what is geothermal energy, how the energy is produced inside the earth, how the geothermal reservoir is formed, the classification of geothermal reservoirs. We have seen low enthalpy, medium enthalpy and high enthalpy based on the temperature. And we have seen the uses of geothermal energy like direct heating as direct use, and we have seen the geothermal power plants for the electricity production and the ground source heat pumps. And we have seen in detail the geothermal power plants, what it is and what are its different types like dry stream which is vapor dominated, liquid dominated which is the wet stream and the binary cycle. All these comes under the natural geothermal reservoir which is hydrothermal reservoir. We have also seen the enhanced type EGS, enhanced geothermal system, which is a man-made reservoir. This is mainly used for the heating up of the buildings and other construction parts. Later on we have seen in this module the advantages and disadvantages of this geothermal energy. Also we came across the global scenario of this geothermal energy, and we have seen the potential of geothermal energy in India. We have seen that mainly the two regions, the Manikaran in the Himachal Pradesh and the Puga Valley in the Jammu and Kashmir is highly or the rich in this type of energy, and we can harness this geothermal energy from this region. Thank you.